see more next year on a normal cadence here on the AWS.
Absolutely.
I didn't even finish.
Absolutely.
Don't worry. We're hopefully working towards that one. And we'll end with you, Darren. Go ahead. What did you think?
Yeah, like it's hard to
Oh, hang on. Whoa. Darren's going to say he loves it because he won an Evo. He's not going to go, oh, it's terrible.
Yeah, I was gonna say it's hard to act that I don't enjoy undergrounds. I think it's just brilliant. Whether you're there to test some new approach and see it fail, it really doesn't matter because it's all experience that you can't get anywhere else. There's prizes to win as well, which is great, but it's really these two guys here on the call that's doing, as you know yourself, right? There's so much work. I've only been minorly involved in other races or trying to set it up, but like any of those cars can go have issues and you have to just react on the spot and bounce with the problems. I thought the way you guys finished with like a marathon race was kind of a testament to all the learnings you've done every fortnight and sometimes every week between yourselves, London, and then back in the States. Whether it's the streaming or the racing or even starting to bring in the Evos, like you guys ran Evos publicly for the first time. They wanted them in the summit sooner, but we just weren't able to get that. You had 4 different forms of tracks. You had John's slightly smaller handcrafted basement track, Dave's Y track that then slipped off into the old track, and then he's got a 2019 track. And John actually had one outside next to in the sunlight, so you could try your model, see if it's really good convergence, if it can do the sunlight. And when you split between the beginners and pros, I thought that was genius. I thought give people who can't get to the leaderboards easily because a lot of people know a lot of stuff, get them it. If people have multiple models and you've got time on the hour, you just run extra models, or even behind the scenes, you'll run extra for people who submitted late or models that didn't work on the day. But I'll stop now because I know I've got finals soon. But yeah, love it. So enjoy your break. See you next year.
That's all right. Guys, I really appreciate you joining us. I'm going to wrap this up, and thank you guys so much. Ray, thanks for joining us, your time. I really appreciate it.
Thank you for having me.
Yes, Darren, aka Debro, thank you so much for joining us. I really appreciate it as well. This has been an opportunity and a pleasure.
Thank you, guys.
So David, as always, thank you for hosting these with me and joining during these crazy times and all the Underground Deep Racer stuff. This was our last official Underground Deep Racer for the year. Do not worry. We will have a schedule. We will plan things in the future. I look forward to the championship. Guys, I really appreciate it. Don't forget to follow along on us. And, let's see who wins this. We have 8 finalists: Carl, Duckworth, Kondoa, JPMC, Drift King, Pochon, Robin, KUEI, and Jokum. So I'm looking forward to it. Hope you guys enjoy it. David?
Can we each choose a favorite?
I'm going to go Robin because, why not?
Robin!
Can't all choose the same.
I'm going with Robin only because I've got some, obviously I lost to Robin. Debro, who you got?
I'm going for Jokum.
Jokum. All right. There you go. You had our official one. We are wrapping it up. Join for the finalists, see who wins that one, and then Werner's keynote. Let's see how that happens. Thank you, everyone. I really appreciate it.
Bye, everyone.
Have a good one.
At AWS. And in just a few moments, we'll find out which developer will take home the most coveted prize in machine learning, the AWS Deep Racer 2020 Championship Cup.
Of the thousands of racers who have competed in the virtual league this year, only 8 have earned a spot in today's Grand Prix final.
Who will join Rick Fish
Come on out, Rick!
and Sola as Deep Racer champions?
Let's meet our 8 finalists. Starting in 8th from the United States of America, JPMC Drift King, representing JP Morgan Chase & Company. Starting 7th, Carl NAB from Australia, representing the National Australia Bank. Starting 6th, Robin Castro from Singapore, representing DBS Bank. In the 5th starting spot will be Condoriano, racing out of India, representing JPMC. Starting 4th is Jakob from the Netherlands, representing Relive.cc. Starting 3rd will be Duckworth from Norway. On the outside of the front row will be Po Chun in CTU, and starting on pole, Quay, also from NCTU CGI in Taiwan.
Let's go.
The Grand Prix final begins in 3, 2, 1.
Go green.
Clean getaway for our top developers, but look at that move to the inside in turn 1. Po Chun grabs the top spot from Quay, but a big pile up a little bit further back in the pack. It looks like as many as 5 cars involved.
Piled up in the back.
Look at that carnage, but it's still not cleaned up with the leaders coming through to complete their first lap. Po Chun around for the first time, leading by just over a second over Quay. The 2 teammates from NCTU, Duckworth trailing about 2 seconds further back.
I got lapped.
Already on the 3rd lap here, Po Chun has the lead in the red car and has built a lead of over 6 seconds over Duckworth. Quay dropping back. Po Chun spins off track. 3 laps complete, working lap number 4 at a massive lead here for Po Chun. Nearly 8 seconds the advantage, but Duckworth closing in. That lead down under 3 seconds now.
Still number 6. How are you so fast?
Po Chun back up and moving again, starting to build that edge. Now around the final corner, taking the white flag, and Po Chun is off track. That opens the door. Here comes Duckworth. Duckworth to the points. Just 1 lap to go.
Unbelievable.
Such a steady race from Duckworth, but now has to fend off Po Chun. Po Chun on the attack, tries to slide up the inside, but contact there. There's going to be a 3-second penalty for that.
Oh my goodness.
Duckworth in the clear, just 1 corner to go. Slides off track. Duckworth in trouble. Here comes Po Chun. Po Chun across the line in first. Duckworth gets going in the nick of time and holds off Quay. That's your top 3. Po Chun, your champion in 2020 in dramatic fashion. Duckworth nearly had it won. Will have to settle for second. Quay comes home in the bronze medal place. Duckworth just moments away from securing the coveted Deep Racer Cup.
Suddenly you drive off. Unfortunate not to be in front in the end, but still, I'm very, very happy with second place.
Your champion for 2020 is Po Chun in CTU CGI.
The AWS Deep Racer League is proud to present the 2020 Championship Cup to our winner, Po Chun. Congratulations on an amazing season and a fantastic final race.
As it all came down to those final few seconds, what was on your mind?
我原本想说我应该要输了，但是没想到最后居然会在对手会在终点前撞到，然后就逆转获胜，就非常的惊讶。
Congratulations on a performance that will go down in Deep Racer history.
Okay, thank you.
Thank you to everyone who watched and competed in the AWS Deep Racer League. We will be back bigger than ever in 2021.
We hope you'll join in the fun and turbocharge your machine learning skills today at deepracerleague.com.
Cause it's hard when you're far from me. it's harder when you fall for me. It's hard when you fall, but it's harder when you fall for me. I've been on the road, I've been taking my time. No lie, cause it's hard when you fall. Cause it's hard when you fall for me. I've been on the road, I've been taking my time. Yeah, it's hard, cause it's hard when you fall. But it's harder when you fall for me. And I'm feeling fresh. Looking at my rollie anytime I flex. All the boys love me and they think I'm fresh. Swag on my cap with the brim flip back. Rolling with my fly girls, rocking baby fat. Dookie chain on, about to get to the cash. Know the Benjamins, keep it so girl fresh. Grills, diamond cuts, flossing in the Corvette. Better come correct if you wanna impress. Keep it fresh. Catch me on the strip, baby, where the party at? It fresh. Looking real fly, fresher than peppermint. Keep it fresh. Got a dope girl pose with my dope girl clothes. Back to the block with a dope girl nose. Dope girl. Yeah, dope girl. Yeah, dope girl. Keep it dope girls.
Everyone knows you gotta work it. You gotta push it. You gotta fight it. You gotta live it. You gotta feel it. You gotta work it. You gotta pump it, pump it, pump it. You gotta pump it. Everyone knows you gotta work, push, 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 push. You push, fight, 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 live, 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 live. You gotta feel it, feel it, feel it, feel it, feel it, feel it. Work it, work it, work, work it, work. Pump, 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 pump it, pump. You gotta pump it. Everyone knows you gotta work, 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 everyone work it, everyone push it, everyone fight it, fight it. Everyone live it, everyone feel it, everyone work it, pump it. Everyone work it, everyone push it, everyone fight it, fight it. Everyone live it, everyone feel it, everyone work it, pump it. Work it, work, work it, work, work it, work, 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 work it, work it, work it, work it, work it.
Fighting makes me wanna get it back. You love it, You love, you love. You love, you love. Your fighting makes me wanna get it, get it, get it, get it. You love, get it, get it, get it, get it. You love, get it back. You love, you love. You're fighting, you're fighting, you're fighting, you're fighting, you're fighting. Makes me wanna get it back. All of your love, all of your love. Want it back. Like I'm a creature, like I'm a creature tonight. Loving you was easy till it all came out. It all came down, yeah. Touching you was something. Without you, I'm nothing, babe. Your fighting makes me wanna get it back. I don't wanna go, I don't wanna do it without you. But every time I look, everywhere I look, there's no you. I don't wanna go, I don't wanna do it without you. But every time I look, everywhere I look, there's no you. I don't wanna go, I don't wanna do it without you. But everywhere I look, every time I look, there's no you. I don't wanna go, I don't wanna do it without you. Every time I look, everywhere I look, there's no you. We will never do life together. No, I don't wanna go, I don't wanna do it without you. Everywhere I look, every time I look, there's no you. I don't wanna go, I don't wanna do it without you. Every time I look, everywhere I look, there's no you. Haters mad cause I stay up in the limelight. Stay up on my grind. Haters mad, haters mad, haters mad. Stay up on my grind like stay up on my grind. Stay up on my grind like yo shifty, 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 yo shifty. You a madman for this, yo.
If there's an upside to this past year of working from home, it's that I've been able to spend it in my hometown, Amsterdam. I can't remember when I was able to spend such an unbroken stretch of time in one place. And it's my place. Amsterdam is a story of people harnessing technology. All these canals, which began centuries ago as a way to direct water away from settlements, became the centerpiece technology that enabled the expansion of a city, the flow of commerce, and ultimately a connection that reached out to the entire world. For me, this beautiful city is a reminder of what becomes possible when you connect people and ideas. It shows what can be done by artists and technologists on behalf of people and communities. All you need, some creativity, the right tools, and some room to build. Technology always moves forward, but sometimes it's also good to look back, to look at where we came from, to understand our foundation, and the building blocks that have propelled us at lightning speed into the world we live in now. Which is why I'm so excited to have found a place that will help me tell the stories of yesterday, today, and beyond.
I'm speaking to you today from the CSM Suikerfabriek, or Sugar City as it is called today. A factory in Halfweg, just outside of Amsterdam. And today it's an industrial heritage site, and it stands at the site of a castle used by the Rhineland Water Board. Sugar City, or the Suikerfabriek in Dutch, was built in 1863 and was one of the many sugar beet processing plants here in the Netherlands. The site has evolved over the years, and today it's used for music, events and retail shopping. And although it has changed a lot, the stories this place tells about technology, resilience and operations are still valuable in the digital world we live in today. These are the evaporation boilers that were used for sugar processing. Equipment like these were managed from a central control room. If it were running today, it would be operating much differently. Modern factories rely heavily on IoT devices, data gathered directly from equipment, and real-time computing to quickly alert when there's a problem. A device like this AWS snow cone could be a one-way for Sugar City, if it was operating today, to collect data as it is coming from the equipment. The snow cone could process the data, store it, and connect the boiler to the factory's alerting and automation systems. This way, the factory isn't bound by latency or transfer speeds of the internet connection. This factory has stood here for over 150 years. It has a lot of stories to tell. We can learn a lot from places like this. We just need to know where to look. It has been a challenging year for all of us. Everyone I know has been affected, either professionally or personally. And I've talked to quite a few of our customers who've been affected in the most dramatic way, with either family members or colleagues passing away. We have a long way to go before we can leave 2020 behind. As builders, we face unique challenges to keep doing what we were doing. But we also have the opportunity to make a disproportional impact, as digital has become the default way to access services. With the success of these essential digital services, we'll continue to expand on that, even if we can return to some form of normal. 2020 has tested all of our systems, physically and digital, and mentally. And with the changing needs and behaviors of our customers, the needs of our applications are changing as well. Just like this factory, many businesses have had to change and adapt in order to survive. It's never been more important to stop, assess your needs, and ensure you're focusing on the right things. At Amazon and AWS, we've been very fortunate in a lot of ways. Although many things are different, not a lot has changed about how we work. Our focus on small, independent teams that are self-sustainable and self-directed set us up for success in these challenging times. And we've seen all around us that many companies who rely on complex supply chains to meet increased demand are having serious challenges. And as such, we're very fortunate at AWS that we're part of a business that relies on robust procurement and fulfillment processes. It allowed us to keep up with demand, even when other cloud providers were struggling. We've been doing remote development for a long time. So we already had the tools, processes, and mechanisms in place to do distributed collaboration for teams that are spread out all over the world. We have a long history to go where the talent is, instead of forcing everyone to come to Seattle. All our engineers are working from home, or actually anywhere where they would like, just not the office. And given the success we had with it, I don't think that's going to change anytime soon. And while Amazon and AWS have been very fortunate to be well prepared for this, many of our customers have not been so lucky. Think about the hospitality and the airline industries. In talking to some of our airline industry customers, they expect that even if we can leave the pandemic behind in 2021, they do not expect to fully recover until 2025. And they expect that long-haul business travel may never return to previous levels. Their cargo divisions, however, do expect to thrive. And I've seen how some of them are pivoting to find new businesses or are doubling down on the things that do work. And there's an interesting analogy with this sugar factory. With the diminishing need for sugar, they pivoted to focusing on storage and packaging. And when that moved off-site, this factory was converted into a retail and event space. But when this factory was focused on only adapting to changes, the other sugar factories in the Netherlands were branching out into other industries. Today, there's 2 significant Dutch sugar providers. But in addition to sugar, one processes other crops like potatoes and onions, and the other one is a producer of bakery ingredients. They diversified to better be able to withstand unexpected hardships like this. Now, we were very fortunate that we had established a number of years ago an AWS disaster response team, whose task it is to immediately reach out to customers who may have been negatively affected by a natural disaster, like earthquakes or typhoons. And as such, we hit the ground running when we saw how customers started to get affected by the pandemic. Personally, I've been working with quite a number of our customers who have been adversely affected to help them get fundamental control over their cost by moving to what I called in the past keynotes cost-aware architectures, so that the business has knobs to turn with respect to scale, reliability, and performance to meet their needs now and in the future. A number of these customers has also seen downtimes as an opportunity to accelerate and innovate. One of the most important ways that technology and the business can work together is by using data to power new experiences for your customers. I want to introduce you to an AWS customer who really embraced this idea. Ava is a digital health company with a mission to advance women's reproductive health by bringing together artificial intelligence and clinical research. So let's hand over the camera to Lea von Biller, Ava's co-founder and CEO, who's recording in her home in Switzerland. She has a great story about the amazing insights that Ava is able to produce for their customers by making new use of the data they collect.
Thanks, Werner. I'm really happy to be here today and share with you insights about how we at Ava harness the power of machine learning, clinical research, cloud technologies, and AWS services to improve women's health. Digital technology and cloud services have transformed almost every aspect of our daily lives. With just one tap, I can order a ride, get a room, share a photo. And of course, digital technologies have also started to revolutionize modern medicine, with AI being able to do really interesting things, such as diagnose fractures or detect atrial fibrillation. However, when it comes to women's health, progress has been very slow. And this is largely due to the lack of funding and to the lack of research in the space. We at AVA want to change that, because we believe that so many women all around the world face unique and often unaddressed health challenges when it comes to their reproductive health, be it in contraception, conception, pregnancy, or menopause. Our vision is to be a long-term, trusted companion for women across their reproductive journey by giving them personalized, data-driven, and actionable insights about their health. And how do we do that? We're doing it by bringing together artificial intelligence and clinical research. For our users, it all starts with the AVA bracelet, a wearable device that collects individual health data about her, including breathing rate, heart rate variability ratio, perfusion, and skin temperature. Every night, we collect more than 3 million data points from each of our customers and integrate that data into their health histories, where our multiple algorithms improve over time, learning each woman's unique menstrual cycle patterns and making individualized health recommendations. In 2016, we've launched our first product, the AVA Fertility Tracker. And we have since then helped over 40,000 couples get pregnant using the bracelet, by empowering them with actionable insights and by giving them a daily real-time fertility indication so they can better time conceptive sex. But we're not simply in the fertility business. What we've actually built is a technology platform for collecting long-term personal health data for women over 5, 10, 15 years and more. And in fact, it is managing this huge data set that is really at the core of our business. So when we started our journey 5 years ago, we put a lot of thinking into how to best set this up and which cloud provider to choose. Because we knew if we were successful, our data would grow exponentially and we would have massive amounts of data to be processed and stored in close to real time. We knew we needed to be able to scale our computing power to manage the daily traffic peaks that result from our users syncing their device each morning. We needed security to protect the sensitive personal health data we collect. And we needed a flexible architecture to be able to add new services and applications on a regular basis. Ultimately, we selected AWS as our cloud provider, especially for the reliability and efficiency of managed services, data solutions like Amazon Relational Database Service, MongoDB on AWS, and Amazon Simple Storage Service that enable us to operate with 300 terabytes of users' health data in a reliable and secure way. The ease with which we can orchestrate services and deploy web applications. And of course, a large community of developers and guidance around best practices to bring it all together. Thanks to our collaboration with AWS, we have the technology we need to accelerate our ability to innovate and to provide new medical-grade services and applications. Following the success of our fertility application, and in line with our vision, we will soon be launching a non-hormonal contraceptive solution. We've also been able to move very quickly to address the current COVID-19 pandemic by developing an early detection algorithm that works for everybody, but is particularly well-suited for women. When COVID-19 hit, we found ourselves in an unusual position. The AVA bracelet was one of the only medical-grade devices on the market with multiple sensors potentially related to COVID-19 symptoms, such as temperature or breathing rate data. We quickly realized that we could utilize our unique clinical knowledge, as well as our personalized understanding of our users' data, to detect anomalies in body temperature, heart rate, and breathing rate in a way that could aid in early detection of COVID-19 detection, even before users realize they're ill or they experience symptoms. This represents a huge step forward in point of care, providing users with actionable insights that can lead them to seek testing or self-isolate to reduce transmission risk. In just a couple of weeks, we developed and deployed a 2,000-person pilot lab in Liechtenstein to collect data and train an algorithm for early COVID-19 detection. Now, we are ready to validate our algorithm on a much larger, novel sample of 20,000 men and women. Soon, we will be opening recruitment for this clinical trial as part of the COVID-RED Consortium funded by the Innovative Medicines Initiative. This project brings together leading academic and industry experts in public health, epidemiology, wearable technology, and machine learning. So how does it work? Participants will wear the AVA bracelet for 9 months, during which time they will receive real-time daily indicators about their likelihood of having a COVID-19 infection based on their personal health data and self-reported symptoms. Our goal is to see if we can leverage the power of AI and personal health data to aid in early detection, as well as provide advice on when to seek testing or other treatment so that medical resources can be conserved and used more efficiently. The speed at which we've been able to support the COVID-RED Consortium and begin clinical trials is a great example of what's possible when a small, flexible company like AVA is backed by AWS with a scalable, flexible, and well-architectured infrastructure. And it's exciting because the clinical work we are doing with the COVID-RED Consortium has utility beyond COVID-19 and has the potential to aid in the early detection of other types of infection as well. Because when we started with AVA, our goal was to improve women's lives for the better by giving them more control and understanding of their reproductive journey. I'm really proud of the work we've done at AVA to realize and expand on that vision, and even more so to see our data-driven and scientifically proven insights applied to the global good of early COVID-19 detection. Thanks to our fantastic team, our wonderful customers, the partners who have supported us along the way, and everyone at AWS who has been part of our journey.
Thanks, Leah. That was great. The thing I really like about AVA's story is how they consider themselves a data company, much more than a device manufacturer. And this really shows how business and technology can work together to create something greater than that they would be able to do on their own. Customers like Brainly did a lot to prepare for events like COVID, but still had quite a few surprises. I talked to them a few weeks ago for a recent episode of Now Go Beyond. They're an online learning system that helps students with their homework. And even before the pandemic, they were growing and built their infrastructure to handle that growth. As schools moved out of the classroom after the pandemic hit, Brainly saw a dramatic increase in usage. In the span of 4 months, they hit a growth target that they'd originally thought would take 12 months to achieve. They grew from 150 million users at the end of 2019 to 250 million users in May 2020. I remember the CTO saying, "I thought we knew our business." The way students learned and worked together before the pandemic was very different after they started and attended classes online. Brainly had built significant automation for scaling up and down based on well-known traffic patterns they had. But not everything was automated, because their long-term scaling had been extremely predictable. And their systems weren't built to handle dramatic spikes in usage. And such services like caching and databases were alerting only a few hours before they degraded, instead of weeks. Cost efficiency unexpectedly scaled better than the infrastructure, and they were able to exploit economies of scale. Their estimation is that it cost 40% less to scale to this level than initially predicted. Another interesting observation they made is that fewer distractions and interruptions in the office led to much better developer productivity. Now, today's developers need the right tools to be able to work outside the office. And it's not just working from home, it's working from anywhere. Your tools should not be part of the heavy lifting of IT. They should enable you to move fast and get the job done, reliably and securely. But as our infrastructure is changing and the way systems are being built is changing radically because of the cloud, we need to update our tools as well. And many of us do not want to be tied to our laptops for developing. And as such, our engineers have become hooked on Amazon workspaces. Actually, an interesting story is that one of my colleagues had a laptop crash. But without easy access to centralized IT help desk, he was forced to move to Workspace as a temporary solution. But he's so happy now, he will not go back. Now, it's typically thought of as a business productivity tool, but it is also ideal for development from anywhere. And you can make multiple workspace configurations with everything set up and ready to go, like your IDE of choice and environment and code and things like that. So this is the equivalent of your cloud developer desktop. Makes it easy to work wherever you are and from any type of device. But AWS Cloud 9 is really the next generation of this experience. Browser-based, limits bandwidth needs, and improves responsiveness. If you work on multiple different projects, you can have different development environments for each of those. And it is used by many teams at Amazon as an alternative to cloud desktops. Cloud 9 has the concept of builders, a series of tasks that build your system, runners, how and where you want to run your system, and debuggers. What was extremely useful in Cloud 9 is that you can share what you're doing live with someone else, which enables, for example, remote pair programming. But because it's a cloud IDE with live sharing features, we saw a significant increase in the usage of Cloud 9. One particular area where Cloud 9 has become extremely popular is in education. For example, Harvard's online CS50 course uses Cloud 9 for teaching computer science. The AWS console and other dashboards are great for exploring services and seeing what they can do. But if you are as old as me, I prefer to use the terminal for common tasks. But I also have a bunch of not so great scripts to then set up the environment that I need for any particular task at hand. So I'm excited to announce today another way where we're meeting developers where they are and giving them the best of both worlds. Today, we're launching AWS Cloud Shell. It is a new service built into the AWS console that gives you access to a Linux terminal inside your browser by just clicking on an icon. And when you start a new Cloud Shell session, it is automatically pre-configured to have the same API permissions as you do in your console. This means you don't have to manage multiple profiles or API credentials for different dev, test, and production environments, like you would normally have if you would work in a terminal. With these credentials being automatically forwarded, it is simple to start a new Cloud Shell session and use the pre-installed AWS tools right away. The AWS CLI, Elastic Container Service CLI, and the SAM, the Serverless Application Model CLI, are all standard inside Cloud Shell. And Cloud Shell is not just an AWS command line interface, though. It is a fully featured shell environment based on Linux too, and includes several other common CLI tools pre-installed, like Python and Node, Bash, PowerShell, Vim, Git, and so on. And just like any other regular shell environment, you can install whichever additional tool you need to get the job done. Yeah, one of my favorites would be the CDK. Unlike a regular environment, though, changes to the operating system don't persist between sessions, so you don't need to worry about cleaning up anything if you accidentally break the environment. However, you do have up to 1 gig of persistent storage in your home directory at no cost, so you can keep your data even if you forget to download it or copy it to S3 when you finish working. Cloud Shell continues our trend in making the right tools available whenever you need them from wherever you are. And we hope you find it a valuable addition to your process of building software and managing infrastructure. Next to the major issues this year of COVID-19 and racial, social, and economic inequalities, battling climate change deserves the highest priority of our attention. Building our infrastructure, systems, and services in ways that minimize the impact on future generations is our foremost concern. Sustainability is defined as understanding the impact of materials and energy we consume, measuring the life cycle of those materials, and apply best practices to reduce the impact of their use. Running applications in the cloud has been more sustainable from day one. A typical enterprise data center will have 15 to 20% utilization at best. The multi-tenant nature of the cloud, which allows for efficient resource sharing, combined with techniques such as the spot market, enable much higher utilization. According to 451 Research, running your applications in the cloud reduces your carbon footprint of your systems by 88%. 61% of the carbon reduction can be attributed to more efficient servers and higher server utilization. 11% to more efficient data center facilities. And 70% can be attributed to reduced electricity consumption and renewable energy usage. This is why AWS is committed to running our business in the most environment-friendly way possible and achieving 100% renewable energy usage for our global infrastructure. In general, sustainability in the cloud is focused on innovation that our data center architects continue to do, for example, to reduce energy usage and water usage. But I'm frequently asked by our customers, but what can we do? I believe that for sustainability of our digital systems, we need a shared responsibility model as well. At AWS, we will continue to innovate in building the most sustainable infrastructure. But I think it's time that we start thinking about what we can do as application builders to get better control over resource usage and start making sure that we can meet the sustainability goals our businesses have set. And because AWS charges by consumption, many times reducing your cost also has the impact of reducing your environmental impact. But I've already seen several cases with our customers where they are willing to spend more to meet their sustainability goals. The AWS solution architects are now available to help our customers with how to analyze software and hardware patterns for sustainability and the sustainability impact of your development and deployment processes. And not just on the architecture side, but also provides guidance with respect to business decisions that could be made, such as considering things like trading the quality of results to use less resources. Looking at factors such as availability, response time, or even accuracy, which can all be adjusted to use fewer resources. Is yet another example of how we as builders need to build controls that make the business to be able to make those kind of trade-offs. In addition to the climate pledge and broader sustainability goals at Amazon, I'm excited that we're taking these steps to help our customers run more sustainable. And one of the interesting recent developments in server design that may help you meet your sustainability goals is the introduction of the ARM processor for data center compute. One of my colleagues, James Hamilton, distinguished engineer at Amazon, once challenged me to count the number of ARM processors running in my office. I believe I came to 17, from printers to cameras, from home automation devices to mobile phones. Everything was running ARM. Only my laptop was running a non-ARM CPU. At AWS, we started developing ARM-based processors years ago, before running it for real compute workloads was a mainstream idea. Initially, we focused on non-customer-facing technologies, such as our storage engines. But quickly, we started to realize that the tremendous performance and price advantages could be had by our customers if we just would bring ARM to the compute engines as well. We had already seen that the popularity of ARM-based platforms such as Raspberry Pi ensured that many Linux distributions and packages would support ARM. Now, the recently released AWS Graviton 2-based instances make it easy to run ARM applications on the cloud performantly. These processors are ARM 3.8.2 compliant, have 64 physical cores, and use 7-nanometer manufacturing with 30 billion transistors. We have ARM variants of many instances, including our memory, compute, and general-purpose instances. We found that high-level languages such as Node.js, Python, Java, .NET Core, .NET 5 typically run without problems. Amazon ECS, Amazon EKS, Amazon ECR, Code Build, Docker, all have support for Graviton 2 instances. I see migrating to Graviton and ARM as a long-term business investment. ARM processors have lower costs and higher price-performance ratio. And for example, the Graviton 2s has 20% lower cost, but a 40% better price performance. And think about that. When was the last time you could see this significantly of an improvement just by changing to a different processor? And now, whether lifting and shifting will work is in general dependent on third-party applications and related dependencies. Even if your code will run on ARM, it doesn't mean that the Python library that you're using, which may actually be a wrapper around some C code, is. To be successful, build pipelines and container clusters need to be created and managed separately for ARM-based containers and binaries. ARM is definitely a platform with a significant innovative future ahead. And I advise every business to investigate whether they are willing to make the investment to migrate. Being a builder means a lifelong of learning. And it is one of the things I truly love about being a developer. There's always a new language, a new library, an open source project, or a new service that will make your head spin and look at development differently. I believe we have the most amazing jobs in the world. We have the opportunity to create something new every day, or to improve something small that makes you smile and proud, and to truly delight your customers in ways that really puts a smile on your face. That's why I love the 100 days of code in the early days of the pandemic, challenging you to learn something new. I learned a new language, Rust. I had worked with teams inside AWS that were using Rust because of its safety properties, but it blew my mind how to do system-level programming in a truly modern language. And we'll talk a bit more about Rust later. Something that saw a tremendous rise in activity was the Amazon Builder Library. It helps developers benefit from 25 years of developing secure and scalable systems at Amazon. Builders clearly took the opportunity to dive deep on hard topics and educate themselves, when otherwise they may not have time for it. AWS Academy provides higher education institutions with a free, ready-to-teach cloud computing curriculum. And one of the programs I'm really proud of is AWS Restart. It focuses on cloud skills for unemployed and underemployed individuals, including military veterans, their families, and young people. We're also working with organizations like the Ready School, who has helped refugees learn coding skills that they either lead to employment, more education, or even creating startups of their own. And by investing in programs like this, we are dedicated to educating a diverse group of future builders who have lived through this pandemic and will be building better because of it. Almost every year at reInvent, I've talked about how, over the years, we've implemented fault tolerance at Amazon. And based on those experiences, what best practice advice we can give you to meet the fault tolerance requirements of your application. But today, I would like to take a step up and talk about how fault tolerance is only one of the means to achieve the more encompassing concept of dependability. Dependability is when the delivery of a service can be trusted with the avoidance of unacceptable, frequent, or severe failures. Now, what is unacceptable is a business decision, not a technology one. If certain failures or rates of failures are acceptable, then the system is still dependable. Dependability has many properties: availability, reliability, safety, confidentiality, integrity, maintainability, and observability. If you think about how to achieve dependability, there are several means to it. It's not just fault tolerance, but equally important are fault prevention, fault removal, and fault forecasting. And we often talk about other properties related to dependability as well. Concepts like robustness. Can your system be dependable in the presence of external faults? Is the system survivable? Can it handle active, in-progress faults? And resilience. Can the system deal with changes? And resilience is a unique property because it deals with 3 different types of changes. There are foreseen changes, like when you launch a new version of your system, or foreseeable changes, like when you move to a new hardware platform. And then there are unforeseen changes, like when the number of service requests explode beyond what you had planned for. Now, in years past, I taught quite a bit how to build evolvable software and how that deals with changes. I remember how I talked to you about how we built S3? We knew that the system under the covers would need to change, either with new orders of magnitude of scale or with the introduction of new features. Evolvability deals with all the properties of dependability. A less commonly known approach to building dependable system is the concept of diversity, which is basically using 2 or more components that have the same functionality, but have been built in isolation from each other. For example, here at Sugar City, there are 2 generators. We're going to take a look at them in a minute. Diversity means that each generator would have been sourced from different manufacturers. But again, this is a business decision based on whether failures would be unacceptably frequent and or severe. One of the interesting things I've learned about this factory is that it only processed sugar about 3 months out of the year. This was to coincide with the sugar beet harvest. They prepared all year for the 3 months that farmers would bring their sugar beets here to be processed. It was so busy that workers had to bring in mattresses and sleep in the corners to have enough time to get everything done. Even though it was regularly 40 degrees Celsius, which is well over 100 degrees Fahrenheit. Downtime during these 3 months would be catastrophic. Whoa, whoa. It's quite an echo here. Although you can also still hear a hum. Even in this derelict factory, it still feels it's alive. Yeah. So electricity was crucial for the factory. In this turbine hall, the 2 generators were used to produce the electricity that powered the entire factory. Unfortunately, in those days, and today, and in the future, faults are a given, as are changes in the system, or impacting external factors. In today's world of digital technologies, much of the thinking that built dependable systems and processes in those days is still applicable today. Just like the sugar factory, every online retailer knows that just a few months out of the year can be important to have a thriving business. A profitable holiday season and the launch of a new product are the times that are most critical to the success of a company. That's why I'm excited to have Nicole Yip from Lego talk to us today. Nicole is an engineering manager working on Lego's direct shopper technology team. She has a great story about the resilience challenges they overcame after their application crashed during the launch of a really cool Lego set.
Thanks, Werner. I'm very excited to represent the direct shopper technology team at the Lego Group here today and take you on our serverless journey so far. At the Lego Group, our mission is to inspire and develop the builders of tomorrow by becoming a global force for innovating and establishing learning through play. As an almost 90-year-old company, we have consistently innovated and reimagined our approach to achieving our mission, and technology has been a key enabler for getting our message out there. We use a variety of services across the company, each fit for the purpose that they were selected for. I'm going to talk about the journey of the team behind Lego.com, specifically the pages where you're browsing for products, redeeming VIP rewards, or completing your order through checkout. We are the direct shopper technology team with engineers in the UK, United States, and Denmark. Our main challenge is typical to the world of e-commerce. The traffic patterns are extremely spiky, and with regular product launches and sales events driving customers to the site all at the same time. This diagram shows our typical traffic patterns on one of our busiest sales days. And every year, the number of visitors to the site keeps growing. Now imagine trying to tackle all of that spikiness and year-on-year growth with an on-premise monolith tied to back-end systems with limited scale. Back in 2017, we had a highly anticipated sales event for the Millennium Falcon set, the biggest LEGO set at the time and an extremely popular product line. On the launch day, we experienced a huge spike in traffic that resulted in our back-end services being overwhelmed, and all our customers could see was the maintenance page. The service that failed the hardest was a small piece of functionality that calculated sales tax. It made a call back to our on-premise tax calculation system, which very quickly reached its limits. At that point, we knew that we were on a trajectory for growth that could no longer be sustained with an on-premise system. There were 3 key drivers that took us to the cloud. Renting the commodities meant that we, instead of maintaining infrastructure that was not a differentiating factor for the LEGO Group, meant we could instead focus that energy on building awesome shopper experiences. And you saw the profiles that I showed before. Having that flexibility to scale to support a very spiky demand profile and having the exact capacity we need when we needed it was critical. And finally, having a composable architecture down to the most granular levels enabled us to have speed to market and also flexibility to keep innovating and pushing boundaries. Here is a high-level view of where we are today. We made the conscious decision to extract and focus on our business logic and decompose that across several layers of serverless services. We backed them by carefully selected third-party vendors who provide specialized services like payments providers and content management systems. Each of our layers is designed to scale automatically and independently to support an ever-changing traffic profile. And this design also allows us to handle multiple squads operating across all parts of the site concurrently. And you'll see why that's important in a moment. Our journey to the cloud started with migrating a single user-facing service, the one to calculate sales tax, and 3 back-end processing services back in 2018, just to show that serverless could work for us. 10 months later, we then matched our existing capabilities with a completely serverless platform that immediately started handling the same level of traffic and transactions as our existing platform. We then immediately started exceeding those rates of transactions and traffic and setting new records every few months. We started off this year with an ambitious roadmap, a growing team, and a platform that was only a couple of months old. And then the question became, could we deliver on that ambitious roadmap with twice the number of engineers, all onboarded remotely, and keep the platform stable, all while handling high season levels of traffic? The answer was yes. And not only have we doubled the number of services in production, we've managed to do so while handling increasingly busy sales periods. To put some numbers up to the growth we experienced in the past year and a half, we now have 3 times the number of engineers in the team, and we've since launched another 36 serverless services, pushing the number of Lambda functions in production over 260. The growing team meant that we had to distribute many tasks previously held centrally by an infrastructure team. So automation has been key to supporting the ever-growing number of squads and application engineers to get their services and features into production, not only at their own pace, but safely. We've moved to a self-service model where possible, for example, creating a script that creates standard integration and deployment pipelines for any new service. The ultimate goal is to develop our application engineers into DevOps engineers who own and operate their services in production. One of our first steps towards that goal was to introduce a standard where all serverless services were to implement canary deployments using AWS Code Deploy, and this gives the automatic rollback when necessary. And that leads me on to serverless operations. We have focused on observability and a fan-out operations model, where our on-call team monitors some key high-level metrics centrally, and then each service has been categorized based on how critical it is to our key user journeys. We then have a default set of alerts that are to be implemented on each service and tuned to the profile of that service by the squad that owns it. This is giving our engineering team a starting point of how to monitor their services in production and not only detect, but react to issues that are happening in their space quickly. The growing team means we can't have tacit standards anymore. The team is made up of engineers at all stages of their careers and with differing levels of experience with the technologies we're using. I've mentioned already a couple standards that we've set, and they define what a good service means to us. They define the hallmarks of a good service that not only uses the latest coding practices and patterns that we've developed over time, but also those guidelines for safer deployments and monitoring of services so that they're easier to own and operate. We have started comparing our standards with the AWS well-architected framework, and specifically the AWS serverless lens. And this has shown that they mainly are in the operational excellency pillar with a little bit in cost optimization and a bit in security. And so looking to what we're focusing on next, we want to define the standards in the remaining reliability and performance pillars. And then we can start looking at making the standard more visible. We want to show our engineers the services that they own, what state they're in, all in one place. And then we can start adding on things like maybe a leaderboard. This should add in that competitive element so that owning a service becomes a point of pride within the team. And then we can start playing with the next level of serverless operations. We have chaos engineering on our roadmap, and this should enable the team to really break apart their services, test out the failure cases for an entire third party, and that means that we can craft our shopper experiences to still be awesome even when part of the platform disappears for a bit. It's hard to imagine that we only started our journey to the cloud back in 2017, but time flies when you're having fun, and we've learned a lot along the way. The name Lego is an abbreviation of two Danish words, leg and godt, meaning play well. And when play is at the core of everything you do, the learnings and opportunities are endless. Thank you.
Thanks, Nicole. What is great about Lego's story is that in addition to providing a more stable platform, migrating from a monolithic design to serverless also freed up engineer time to work on new features. Like Lego, Zoom is another great example of how a company used smart application design to scale quickly as they were flooded with traffic during the pandemic. Just like Brainly, they had well understood traffic patterns and even relied on manual scaling on AWS because their traffic was so predictable. But after the pandemic hit, they quickly experienced a 30x growth. One of the really smart decisions they made before the pandemic was to split their application into different services. They broke the part of the applications that handled the management of meetings, like authentication and scheduling and starting the meeting, from the part of the application that streams video. Meeting management is a pretty light task and isn't dependent on latency. On the other hand, streaming video requires a significant amount of bandwidth and compute power, and it needs to be close to users. Before the pandemic, their management component had sometimes more traffic than the streaming part had. After the pandemic hit, they relied on scale of AWS and our ability to keep up with capacity needs to add media servers to handle the video and streaming for people around the world. Over the last several months, there were times when their engineers were adding 5,000 to 6,000 servers a night on AWS. And just like Brainly, Zoom also saw customer behavior change because of the pandemic. When they started out, Zoom primarily provided services to business users. Today, they see significant usage by individuals and educational institutions. And this affected the design of their application and how they approached scaling. Take education, for example. Before the pandemic, only a few teachers at a school might be using Zoom at the same time. Today, in a district that is fully remote, every teacher is likely to be running a meeting in parallel with other teachers. And these type of changes meant that Zoom was regularly hitting new bottlenecks and challenges that they hadn't seen before. But because of their architecture, they were able to quickly address them and even add many new features, while handling extreme scaling. By following best practices and decomposing their system into separate components that each had unique scaling, performance, and security requirements, Zoom designed a system that can adapt to these unexpected changes. And they've been able to succeed and provide a service that is essential to their customers. If you follow cloud best practices around microservices, load balancing, multiple availability zones, you're likely in great shape from an application architecture perspective. But what about the application code that actually runs within the system? When it comes to dependability, a step that is often missed is the logic of the application code itself. Now, almost all developers today write unit tests and provide code reviews to look for errors as they're developing. But at AWS, we take this a step further and use tools based on mathematical logic to prove that our code does only what we want it to do and nothing more. This is hard, it's time-consuming, and something that most businesses don't have the ability to invest in. For example, one of our teams had recently published a paper that outlines how we prove the correctness of the KMS protocol. When we say that we have the most secure global infrastructure, this is rooted in the continuous work we do to demonstrate this claim with mathematical rigor. We do this to answer the most important question. Are we really protecting our customers? I want to talk to you about this more, but before I do, I want to tell you how I think about reasoning. Reasoning is the action of thinking about something in a logical, sensible way. As engineers, we reason out problems all the time. We design systems to solve complex problems with many variables. Again, look at this factory. To produce sugar, there's a multi-stage process. Farmers bring beets to the factory, where they then are washed with high-pressure cannons, then they're sliced into small strips before being combined with hot water during a process called diffusion. The diffusers create a sort of juice that's put in an evaporator and spun in a centrifuge to separate the sugar from the water. After all this happens, the sugar is packaged and shipped. Now, this process is not all that complicated. It has a distinct start and end, and the steps in between have to be followed exactly in that order. If you put it in a flowchart, it would be pretty simple. And when Jean-Baptiste invented this process in the early 1800s, he had to reason out each state based on the inputs it had and the output it created and what was required to get to the end state. This is the same process you're using when you're developing software. You create functions, each with an input and an output, and they pass information to each other. And when your program is small, it's pretty simple to see how data is going to move from one function to another. You could easily create a flowchart to describe all the possible paths your application logic would take. But in reality, most applications aren't that simple. Or if they are, they don't stay that way for long. In most applications, there are hundreds to thousands of unique functions, which each taking the different set of inputs and creating an output that is passed on to another function. And instead of always being followed in a specific order, functions can call other functions, depending on what they're asked to do or the specific of the data that was passed to them. Now imagine the complexity of the flowchart that you would need to build to represent all the paths that your application could take. There's no way that a human can possibly know all of this. And that's where the field of automated reasoning comes in. Automated reasoning can also be called computer-aided development. Automated reasoning comes in many forms, and it is simply the process of using computers to prove anything that can be described with complex logic. In fact, this is one of the first major use cases for early scientific computers. Some of the first programs ever written were attempting to find proofs in mathematical logic. One form of automatic reasoning is formal verification. Formal verification involves converting the logic of an application into a specification and then mathematically proving that the spec does exactly what it is supposed to do, no matter what. It's very expensive and difficult and time-consuming. It only makes sense for applications where the cost of failure is truly devastating. Organizations like NASA use formal verification to ensure that space missions that cost hundreds of millions of dollars and risk people's lives don't fail because of software bugs. Intel invested heavily in formal verification after the floating point bug in early processors caused a massive recall. Today, all the leading chip manufacturers, including AWS, develop processors using formal verification tools. Another area where we're using formal verification is in one of my favorite services, Amazon S3. When we pioneered S3 in 2006, we built it because we knew customers wanted storage for the internet. Our top design priorities in 2006 were elasticity, reliability, durability, and performance, because that was what mattered to our customers. Given that nobody had ever built anything of this scale before, we relied on fundamental distributed systems concepts to make sure we could meet those guarantees. In fact, I think S3 is the only product we ever launched with a list of distributed systems concepts in the press release. But with the knowledge that failures of components, big and small, are a given, remember, everything fails all the time, we need to balance the trade-off between availability and consistency, based on the now infamous CAP theorem. Given the applications we initially target, we decided that availability, always be able to access your object, had a higher priority than getting the last update to your object. And there could be a small window of time between when you updated your object and when all read requests would give you the updated data. The data was there, stored reliably and durable, but the metadata was eventually consistent. As S3 has evolved into a more generalized storage engine, it is now used for many real-time processing applications, like, for example, analytics on top of a data lake. The majority of S3 access now is machine to machine instead of human to machine. Now, it turns out that machines have a much harder time reasoning about eventual consistency than I ever anticipated. And there's the law of preservation of complexity. If you need strong consistency on top of an eventual consistent system, you need to do the work. Over time, we learned that quite a few of our customers were building that complexity into their applications to achieve strong consistency. We knew that if we did that work for them, life would be a lot easier for our customers. To achieve that, we had to introduce new protocols for cache coherence and distributed systems communication in the request path for S3's metadata storage. This allowed us to ensure that every S3 index storage service always has the latest metadata and was in sync with the cache servers. And we had to introduce all of this while continuing to run S3 without impact to availability or performance. S3 had to evolve into the next generation without our customers being impacted in any way. So while we did traditional performance, integration, load, and unit testing, we knew there were some edge cases that this would not be sufficient for. For example, when read operations race with write operations at very high concurrency on a versioned item, the system can enter edge states leading to eventual consistency again. And this is where formal verification comes in. We relied heavily on it and explored millions of combinations of states through formal mathematical models. We would never have been able to prove to ourselves that we covered all edge cases without formal verification. And because of all that, we are now able to confidently announce that Amazon S3 delivers strong read after write consistency for any storage request, without changes to any performance or availability, without sacrificing regional isolation for applications, and at no additional cost. The field of automated reasoning is having an impact on AWS services in many other ways. I've always talked about security, and you've heard me say it every year: encrypt everything. Security is the most important thing that we can be focused on for our customers, and I think it's something that should be on top of the mind of every customer themselves as well, no matter what they're building. When you're developing something new, it is possible to build a system that unintentionally allows access you didn't intend on. At AWS, we asked ourselves, how can we help customers with this? And we've been making significant investments into security-focused tools that use automated reasoning to help detect security gaps. One of these is the recently announced VPC Reachability Analyzer. In AWS, it's amazingly simple to set up a network. It is truly something that impresses me to this day. And if you need to isolate different parts of your application from other parts or from the internet, I can easily do that. I can create a network echo, a security group, or a subnet to isolate these parts from the network. But just like my application logic, the logic of a network increases in complexity the more work you do on it. Most workloads on AWS of any complexity have many subnets, many network interfaces, many security groups, and often all these things reference each other. If you're trying to trace the path from one end to the other, it quickly looks like the flowchart logic problem we had with our application earlier. And that's why we built the Amazon VPC Reachability Analyzer. The Reachability Analyzer uses the same automated reasoning processes to look at your AWS configuration without sending a single packet. It can tell if your system is doing what you want it to do. You can use it to troubleshoot why you can't reach one server from another. With the Reachability Analyzer, you only need to tell us what rules you want to validate, and we automatically build the logic to test and verify it. This is just one of the many tools we offer to customers that are powered by automated reasoning. And the more complex your applications grow, the more important tools like this are becoming. What all these tools have in common, though, is that we make it easy to define rules and test them, because they're based on configuration. The S3 block public access feature allows you to configure bucket permissions as long as they don't provide unrestricted access to the internet. Our AWS IAM Access Analyzer validates that your IAM policies only allow what you intended. With automatic reasoning-powered tools, you tell us both what the rules or policies are, and then you tell us what you want to verify. All of this is powered by technology developed by the AWS Automatic Reasoning Group, a technology called Zelkova. Zelkova translates policy into precise mathematical language and then uses automated reasoning tools to check their properties. These tools include automatic reasoners called satisfiable modulo theories, SMT, which automatically prove or disprove formulas over constants, strings, regular expressions, dates, and IP addresses. Zelkova makes broad statements about all resource requests because it's based on mathematics and proves instead of heuristics, patterns, or simulation. Next to the services we already discussed, it's used in AWS Config, AWS Trusted Advisor, Amazon Macie, Amazon Guard Duty, AWS IT Device Defender, and more. One of the most important benefits is that users can leverage these tools to help identify gaps in the design phase before any data is exposed. Furthermore, this technology is automated, removing manual human intervention to help provide greater scalability. And finally, it is provable. By converting the problem into a logic-based mathematical equation, it can be proven with mathematical certainty. Now I'd like to change it up for a minute and talk more about how and why we build the things the way we do at AWS. At Amazon, we have a long history of allowing our engineers to pick the tools that work best for the problem at hand. We have a number of centralized supported languages and tools, but we do not force them on anyone. For example, when we needed to do fast UI prototyping for Amazon Fresh, Ruby on Rails was the best tool for that, even when we knew it wouldn't be the language used to scale it up. Mark Brooker gave a great talk at reInvent called Creating Technology Standards at Amazon, where he talks about the trade-offs between using what's familiar and safe, Java or C++, and what may be new and risky. He makes an important point here that's worth paying attention to. the time to develop software is relatively small compared to the time your software will be running and needs to be maintained. As such, when the team decided to develop the next generation of a load balancer in Rust, it was not about what was easy and comfortable, which would have been Java or C++, but what would be better for the long-term success of the system. Next to having great safety features and no garbage collector, the main driver for choosing Rust was that it's a great language for using automatic reasoning and formalification of the application logic. We continue to improve our reasoning tools, and because of that, the team preferred to take the approach of learning a new language to build a foundation with the support of automated reasoning. This allowed them the benefit to prove that their code was doing exactly what they intended. And because of the ability to enable verification, Rust has become extremely popular in AWS, and more of our systems are written in Rust, especially those systems required to build dependable, secure services for our customers. Another area of dependability deals with usability. In essence, what if there are faults in your input data? How are you dealing with faults in general? The fault handling paths in your code are probably not frequently exercised. So how can we be sure that the application will continue to be dependent or dependable regardless what you throw at it? Similar to automated reasoning, fault injection allows you to discover these unknowable unknowns. One way this is done with application code is fuzz testing, or fuzzing. Fuzzing works by sending bad data to your application in a way that tries to make it crash. Imagine a form on your website, or an API that accepts data, or even a mobile phone application. What would happen if your application will send malformed data that causes errors? Or what if this happened maliciously? This is exactly what happened in the case of Heartbleed a few years ago. The OpenSSL library was making assumptions that during a heartbeat request, the server should send exactly what was requested. This bug originally discovered by fuzz testing because the fuzzer made a malformed request and the offending function happily returned it. And because of things like this, we're using fuzzing extensively at AWS and use it to test both our APIs and our code itself. But even if your code is perfectly written, hardware fails, packets get dropped, and unexpected traffic spikes happen. Even well-built cloud applications today can depend on dozens of services and components all working together. And failures can happen at every level. To understand how your application will behave when these events happen, the best form of testing is chaos engineering. Now, this isn't a new idea and has been around for quite a while. Netflix popularized this concept many years ago, and a tool they built was called Chaos Monkey. The goal of chaos engineering is to understand how your application responds to issues by injecting failures into your infrastructure, usually running against production systems. Chaos experiments can include generating a baseline traffic load against the system, adding latency to all database calls, and then validating timeouts and retries. And unlike automated reasoning, we believe that chaos engineering is for everyone, not just shops running at Amazon or Netflix scale. And that's why today I'm excited to pre-announce a new service built to simplify the process of running chaos experiments in the cloud. AWS Fault Injection Simulator is a fully managed chaos engineering service that makes it easy to discover vulnerable paths in your applications. AWS FIS helps developers easily set up and run controlled chaos engineering experiments across a range of AWS services. FIS gives you the ability to inject faults, such as latency or failure of underlying compute networking databases and more. That includes control plane level faults, such as API throttling and server errors, that weren't previously possible for customers to do this in the cloud. And FAS makes it easy to run safe experiments. We built it to follow the typical chaos experimental workflow, where you understand your steady state, set a hypothesis, inject faults, and monitor your application. When the experiment is over, FAS will tell you if your hypothesis was confirmed, and you can use the data collected by CloudWatch to decide where need to make improvements. FAS removes the barriers to adopting chaos engineering. I see a lot of benefits for incorporating chaos engineering into your business. From running game days or incorporating chaos experiments into your CI/CD workflows, most people think about chaos engineering for resilience. And that's true, but it's also performance improvements you can make. It is the blind spots that you can catch in your monitoring. And perhaps the most underrated is the experience your teams will get learning how to respond to infrequent but critical events. Mean time to resolution is not just about your architecture and automation, but it is also about the operational muscles that you build and exercise over time. There is no better way to test your system than chaos engineering. And with FIS, you won't need to be an expert to incorporate it into your organization. AWS Fault Injection Simulator will be available in early 2021 and will include the ability to run fault actions against services such as EC2, RDS, ECS, EKS, and more. Out of all the things we're announcing this year, this is the one that I'm most excited about. By offering this as a service, I believe that we can have a massive positive impact on building more robust, more durable, and more dependable systems in the cloud. When we talked about the history of dependability, I mentioned systems theory. A related field of that is systems control theory. It has been crucial in building many dependable industrial and other systems. The most important pioneer in this field was Professor Rudolf Kalman. In 1960, he defined concepts such as whether a system was controllable and observable, or actually unobservable. To be observable is something we know as software engineers all too well. How can you infer the internal state of a system from its outputs? These can be functional outputs like voltage and amperage of the turbines, or non-functional output like the turbine temperature sensors or rotation speed measurements. And this is what we try to achieve with the observability property of a dependable system. How can we infer the internal state of our digital systems from its outputs? Which can include both functional, replies from API calls, for example, or requests to other parts of the system, from non-functional information that we collect through other means. We've been monitoring systems for years. And I remember the earliest monitoring tools came with Unix, VMstat, syslog, netstat, etc. And it wasn't until the late 90s that tools like Nagios and RRD tool became popular. Monitoring is for operators. Just like this factory, an operator would stand in front of this dashboard to watch a gauge start to get close to red, or lights would start flashing whenever there was a problem. Monitoring means that you already know what is important. You think, have all the data you need, and you're just watching it, and get an alert when it goes out of spec. And this is possible for a factory like this, because relatively speaking, there wasn't a lot they could monitor. The generators were the most important thing. which is why all the dashboards were there. The equipment that was processing the beats was all managed by people who worked with it day in and day out, and could tell when it wasn't cutting as well as it had before, or if it started to hum in a different way. A factory like this is a living, breathing thing. And when your workers spend literally all day here, they know when something is not right and when it's going to break before it does. It's a bit like the experienced car mechanic that just needs to listen to your engine to tell you the crankshaft is about to go out. He has a pair of magnificent sensors, of course, and a lot of experience how to interpret output and thus its internal state. However, if there is a car he hasn't seen before, or a problem sound that he has never heard, his experience doesn't help that much. But in our world, what happens when everything is automated and you're not working with the same equipment day in and day out? Or when your ears and eyes are not sufficient? Classical monitoring deals with two questions. What is broken and why is it broken? Monitoring uses a predefined set of metrics and logs to determine known failures. In general, with monitoring and alarming, you can't predict when things will fail. You can only take action when they do. And it's why we used to call people who monitor these systems operators and not engineers. The generators here at Sugar City are extremely complex. It is unlikely that the operator of the dashboard knew how to repair it when something went wrong. But they did know when to sound the alarm and gauges moved to where they weren't supposed to go. As systems continue to increase in complexity, it is impossible to put every important metric for that system on a single dashboard that the user watches. Think about everything that goes into a modern application. There are metrics for the servers, containers, and functions that you're managing. Your application has counters and logs for all the work it's doing. You may have anywhere from thousands to millions of customers, all which have data about what they're doing and how they're interacting with your application. It is impossible to put all of this on a dashboard that a human watches to define alerts for each of these metrics to tell you when they're going out of spec. At Amazon, we've been on a 25-year journey to improve the processes of managing our systems. And we've long left the notion that just monitoring was sufficient to manage our systems. We've embarked on a holistic approach to operations, from collecting massive amounts of data and logs, to how we analyze them, to how we solve and talk about problems when they do happen. And this is what observability is all about. How can we make sure we have the data, the tools, and the mechanisms to quickly resolve problems in a fundamental way? How can we, without reaching into the system, infer its internal state from the data that we have? At Amazon, our most important drivers have always been customer-centric. Find and resolve problems before they impact customers. Understand the impact on your customers when you couldn't prevent it. And fix the problem so that it never happens again. Observability centers on three enabling technologies: metrics, logging, and tracing. All three are important, but serve different purposes. But I do think logging is the most fundamental one to get right. Back at the first reInvent, I made a bold statement. I told you to log everything, and I meant it. Log everything. Logs are the source of truth for what's going on at any given moment inside your infrastructure. At Amazon, Every service, from the hypervisor to network gear, generates logs that are indexed, compressed, and stored durably. We've gone through a few different log collection systems at Amazon over the years. In the early days, we were mounting NFS servers and writing directly to logs across the network. And we were digging through those logs with bash, set, scut, and org. It was painful and time-consuming, but it was the best option at the time. And as we grew and matured, we built a custom client that stored logs in S3. And this made it easy to get logs off our servers and store them durably. To search for errors and to generate ad hoc metrics, we queried those logs with a distributed Hadoop cluster. And this was significantly more scalable than a mounted file system parsed with Linux commands. But every system grows in complexity. Our largest applications are made up of hundreds of microservices, each potentially generating terabytes of logs a day. Using Amazon EMR to query the logs for those services could take hours. So we took everything we'd learned so far and we created CloudWatch logs. With it, you have a single pane of glass where you can view all logs from every service, every container, and every application that you monitor. You can search your logs for specific error codes, filter them based on different fields, or create alarms for different conditions. It's a powerful service, but it's still just the first step. When building an end-to-end observability system, you need logs, metrics, and tracing. If your logs are the source of truth, the metrics that you monitor and graph should come from your logs. One of the most challenging things for software developers, however, is especially if they're disconnected from operations, is to create metrics in a monitoring system. And this is why when you ask an organization what metrics they're monitoring, they'll start talking about system-level metrics, like CPU utilization, or service-level metrics, like number of requests. Those sort of metrics are usually collected automatically for you by AWS, or they're modules that are built into your monitoring application. For Amazon, we heard from our developers that it was too difficult to publish metrics. And there are lots of ways to get metrics into a system, but they often require configuration or additional dependencies and libraries that you need to keep up to date. We needed a system that made creating metrics dead easy. So we stopped and asked ourselves, what's the easiest way for a developer to write data? Well, anyone who's written code without a debugger knows how easy writing to standard out is. And you don't need any libraries. You don't need any dependencies, and there's no configuration. We let our developers define, graph, and track their own data by just building a string and writing it to standard out. And because we're already logging to standard out, we can generate JSON and have it forwarded to CloudWatch logs. We're doing this through logs instead of creating a new metric, because this typically ends up becoming high cardinality data. Now, one of the challenges with allowing developers to create arbitrary metrics at Amazon scale is the level of cardinality it creates. Now, cardinality sounds like a complex topic, but it's actually relatively simple. The total number of unique entries in your data, the higher the cardinality is. Now, let me show you an example. If you're familiar with time series databases, this might sound familiar. Each event has one or more dimensions associated with it. Suppose I have a CloudWatch metric called disk-free bytes, whose dimensions are Amazon EC2 instance ID and the OS mount point, or a drive letter. This has a cardinality of 2, because there are 2 unique metrics, one for each drive. If you have 100 instances, each with 2 drives, then the cardinality of this is 200. Now suppose I have a CloudWatch metric called response latency, whose dimensions are the service instance ID, the customer ID. And suppose that I have 100 servers and 1 million customers. The cardinality of that metric will be 100 million. Creating 100 million metrics in CloudWatch will be rather expensive, inefficient, and difficult to analyze. Now suppose we have thousands of hosts, millions of accounts, and billions of records. The level of cardinality in a dataset like this makes it impossible to use standard metrics and tools to investigate problems and to understand the impact of events. Graphing individual data points also loses the context of a metric. Imagine a request log that measured which server took the request, which account made it, and how long it took. If you graphed requests, account, and time individually, there's no way to cross-reference them. All of the details and relationships that are in the logs are lost. If there's a fault, there is no way of telling which server it came from, or more importantly, which users were affected. You won't be able to tell if the faults happen for all requests or just specific ones. But since now you have all your data in one place, you can start to understand how your metrics interact with each other. And this is where the real cool stuff happens. Let's say you're monitoring your API and you have a graph like this. There's probably a few questions that you're going to have to answer right away. Which API is failing? How many customers are impacted? Which customers are impacted the most? Is it one bad host or multiple? Which shard, petitions, buckets are having issues? Finding these answers in high cardinality data is exactly why we built Contributor Insights. With Contributor Insights, you can analyze logs to dynamically extract and report on contributor data. Our goal is to make it easy to take a graph like this and to show you what's contributing to the change. You can see metrics about the top-end contributors, the total number of unique contributors, and their usage. For example, can you find bad hosts? Identify the heaviest network use, or find the URLs that generate the most errors. And because your metrics are related, we can graph and report on metrics as they relate to each other. Now let's take our API faults example and show you how Contributor Insights lets you find out what the problem is. Let's start with a series of logs that just include a few fields: URI, host, customer ID, and whether the request failed or not. Using CloudWatch alarms, we get an alarm that the number of API failures is above a value that we defined. So we open Contributor Insights and look at a few rules that we have already defined. First, we can look at the rule that shows top 5 failures by request type. So it doesn't look like the problem is specific to any API. Now what if we look at it by host? So host A has the failure. Let's say we fix it and want to know which customers were most impacted so we can contact them. You can build whatever rules you need to understand which metric is contributing to the behavior of your application. If you needed to reference these regularly, you could generate persistent graphs from these rules and add them to your dashboards and alarms. We're providing built-in rules that you can use to analyze metrics from other AWS services. For example, with DynamoDB rules, you can quickly determine which items or partition keys are the cause of any throttling that is happening in your database. With Contributor Insights, you have the power to understand cause, impact, and blast radius of faults quickly and easily. This re:Invent, we also announced Amazon DevOps Guru. DevOps Guru takes the expertise that we've built from operating infrastructure and detecting failures over the last 20 years into a service. It uses machine learning to identify potential issues inside of your account and also provide links to recommended fixes. Available through the console, you can search and visualize operational data across Amazon CloudWatch, AWS Config, AWS CloudTrail, AWS CloudFormation, and AWS X-Ray. For example, DevOps Guru can predict when the amount of data in an RDS database will exceed your provisioned storage. This would have been great for Brainly during the early stages of the pandemic, since this was one of the services they were scaling manually. It's also recommended changes to instance sizes and configurations before an application runs out of resources. Now, the last requirement of an observable system is tracing. Most application requests involve many services working together to fulfill the request. Even simple 3-tier apps have to pass through a load balancer, 2 servers, and a database. When working on a distributed system, tracing the source of intermittent and undetermined failures can be extremely difficult. And this can be mitigated by the use of a request ID that's passed through every layer of your stack. A trace ID is a unique identifier that is stamped on a request by the front door service. From there, the trace ID is propagated to every other service the request touches. If you've ever logged a support ticket with S3, you've been asked to provide this. For S3, the XAMZ request ID is an ID that's passed to every one of the services that make up S3. This allows us to correlate logs between different backend services. It helps us understand exactly which hosts and services serve the request, to find any errors associated with it. Tracing provides you with the ability to understand exactly what happens throughout your entire system. But let me repeat this. You must pass the trace ID between your tiers and put it in your logs. We make extensive use of canaries to monitor our systems. The term canaries actually comes from coal miners. They placed canaries in the mine to know when there was a problem. And because they're smaller and more sensitive, the canary would get sick and stop singing before any of the miners do. For application monitoring, your canary has the same purpose. Canaries perform the same actions as your customers. They continuously verify your customer experience even when you don't have any customer traffic. Canaries should run continuously, and especially during deployments, and alarm any time there is something unexpected. Even if your application hasn't failed, a canary can give you an early warning by alerting when something took, for example, longer than expected. And to build your own canaries, we have CloudWatch Synthetics. Canaries built with CloudWatch Synthetics and Node.js scripts that run as Lambda functions in your account. They work over both HTTP and HTTPS and can test for UI components by providing programmatic access to a headless Google Chrome. One of the great things about building canaries with CloudWatch Synthetics is that it integrates with CloudWatch Service Lens and AWS X-Ray to provide a graphical end-to-end view of the services in your application. Now, I would like to introduce now Becky Weiss. She's a senior principal engineer who worked on many of our systems, including AWS IAM, Amazon VPC, and Lambda. Becky is one of the many experts we have on monitoring. She has some insights into how Amazon engineers think about data and why it's unique.
Thank you, Werner, and welcome to all you reInvent attendees. My name's Becky Weiss. I'm an engineer at AWS, or as we like to call it here, a service owner. And it's my honor to give you the AWS service owner's perspective on this topic of monitoring and observability. Now, if you've ever read anything about how Amazon does business, you know that a principle sitting in the middle of everything we do is customer obsession. And that principle doesn't stop at our product roadmap. Rather, it extends into every aspect of how we operate our services. And yes, maybe even especially, how we think about the eventuality of failure. Everything fails eventually. You know that. You design in a way that expects it. And for me and for the many talented operators that I get to work with at AWS, the name of the game is whether we can see these signals of impending failure before our customers actually experience failure. So how do we do that? Well, we've got our logging system, we got our graphs, we got our dashboards, we got great tools, we continually invest heavily in those tools. We're never done. And you might be expecting me to say next that it's all automated. And maybe it'll surprise you to hear this from an AWS engineer, but automation is necessary, but not completely sufficient for operational excellence. Don't get me wrong, automation does play a large role and we rely on it heavily. So what's the rest of it? Mindset and experience. The good old-fashioned practice of a human brain doing what the human brain does, looking for patterns and being curious about what it sees. We train our operators to be optimistic pessimists. They're optimistic about the business and the ever-expanding universe of possibilities it creates for our customers. But we're pessimistic and curious when it comes to operational health. For a couple minutes, we're going to have a little bit of fun. I'm going to take you into the human side of all of these things that we measure, plot, and chart. I'm going to show you graphs like the ones we see, take you through what we think about them and the questions we ask. And to do that, I'm going to take you through 3 contrived scenarios. These aren't real graphs. I actually drew them by hand, but they're similar to the ones we see, and I'm going to take you inside our brains as we look at them. Here's our first fake graph. Well, we're privileged here at AWS to get to work with a lot of graphs shaped like this one. I hope you are too in your business, because this graph shows more volume over time. That's great. That's business success. All right, now I'm going to show you a different graph for the same service. This graph is measuring something where more of it, a higher value, is worse. Could be latency, could be other things that negatively correlate with your customer experience, like maybe how long it takes to complete a workflow or process a chunk of data. So what do I see here? Well, I see that as my business grows over time, this metric's growing too, and that's bad. And not only that, but it's getting more variable, and that's bad too. So now I can't tell you exactly what's going wrong here, like it's fake. I literally can't tell you that. But at AWS, based on our experience at scale, I could almost guarantee you from a graph like this that we're approaching some kind of constraint, a limit, contended resource, maybe a new pattern that we didn't know about before. And we might even be starting to bump our heads on it. Even if from a customer's perspective, things are still mostly fine. So we are always actively looking for shapes like this on our dashboards, because sometimes these things do take quite a bit of work to find and fix, and we make those investments. Okay, here's our second graph. So we follow best practices. Our service runs canaries that automate end-to-end scenarios that ensure they're working. Yours should too. We talked a little bit before about CloudWatch Synthetics is a great tool to help you do this. So we have a graph of failures, and looks like we failed a run. So you review it, maybe even know why. Like maybe you knew that a direct dependency of yours was having a problem during that minute. But again, let's look at it through that mindset of that curious optimist pessimist. There is a lot of empty space in this picture. So I know what happened during that 1 minute. My canary failed is what happened. But what about all that other time? Well, I don't know. Could be good news, could be bad news. No news could be good news because it didn't fail. Could also be bad news because maybe the canary couldn't even run for some reason. I don't know. And we don't like not knowing. So if we see a graph like that, and it's something we monitor and care about, we want this graph instead. We want that canary posting a 0 value when it runs and succeeds, because then we know that no news is bad news, so we can take action. Okay, final example. I'll show you a little bit of good news. This one looks good, right? I'm measuring my latencies in percentiles. I've got your 99th percentile here. I've set an alarm threshold that's meaningful to me and my customers, and pretty good. Yeah, great job. And you know what we would do with a graph like this? We'd lower the threshold. Why did we lower that threshold? Well, because typically the original threshold, we would have put some thought into it. We would have set it well within the bounds of what we've determined to be an acceptable customer experience. So our customers were fine with anything under that original line. Well, once again, a lot can happen under that line. The graph could go like this. And even if our customers wouldn't have been affected, it's a signal for us curious pessimists that something changed. We want to know what that is, maybe do something about it, if there's a new constraint being quietly encountered. Okay, now all that might have just looked like obvious common sense. You know what? It is. But the reality is when you go around and you look at the various approaches to operations out there in the world, there is a wide range. Everybody's got their metrics around latency and service faults and great tools, but what about your mindset? Are you measuring the things your customers care about? And if it were to change, would you get that signal? Are you looking at that data like a curious, optimistic pessimist? The operationally trained brain is primed to ask these questions. I personally find operating AWS services with that mindset to be one of the most interesting and rewarding things I've ever had the opportunity to do. And if you approach operating your own systems with that same sense of curiosity, I bet you'll find the same over wherever you are, doing whatever it is that you do in the cloud. Thank you very much, and have a wonderful reInvent. Happy operating.
Thanks, Becky. I think you're absolutely right. At the end of the day, all these systems are being monitored by humans. And we're all just guessing what metrics we think we're going to need and where they should alarm. For example, when your metrics fall out a particular range for a certain time period. We talked a lot about CloudWatch today, but when it comes to collecting and visualizing modern operations data, there are a few open source tools that have become very popular. As part of the Cloud Computing Native Foundation, or I actually say that wrong, it's the Cloud Native Computing Foundation, Prometheus is a tool that makes it easy for customers to monitor container environments at scale. Grafana is an open source project for interactive data visualization services used for monitoring and alarming that's commonly used with the Prometheus open source project. Grafana supports multiple data sources such as Prometheus, Amazon CloudWatch, AWS X-Ray, Elasticsearch, and AWS TimeStream, allowing for the creation of dashboards and alerts from multiple sources. Although it's easy to deploy a single Prometheus or Grafana server on AWS, it can take weeks of work to scale across multiple servers and configure the entire environment for high availability. That's why I'm excited to announce Amazon Managed Servers for Grafana and Prometheus. Using these services, we'll manage the provisioning and setup of Prometheus, along with, of course, ongoing maintenance and scaling operations. The Prometheus query language is optimized for large volumes of data, commonly in container monitoring. This makes it easy to search and group metrics, such as CPU memory and latency, at a granular level so that container issues can be isolated and alarmed on quickly. Engineering teams can use the same familiar Prometheus query language to filter, aggregate, and alarm on metrics and quickly gain performance visibility without any code changes. The Amazon Managed Service for Grafana makes it simple for engineering teams to query, visualize, and alert on data sources such as metrics, logs, and traces, no matter where they are stored. These services are available today as a preview on AWS. When it comes to observability, we talked a lot about CloudWatch and other AWS services. But AWS isn't the only company building these services. And I've always said that AWS is so much more than just the AWS services. And I'd be remiss if I didn't recognize all the tools being developed for our complete monitoring and alerting ecosystem. We have great partners who are also operating in this space, like Sumo Logic and Splunk and Datadog and New Relic and AppDynamics. But all these have a different approach to collecting data. And it can be challenging to combine the different approaches, which is something the Cloud Native Computing Foundation is trying to create a foundational approach for with the Open Telemetry project. That's why I'm excited to announce that the AWS distro for Open Telemetry is now generally available. As part of the Cloud Native Computing Foundation, Open Telemetry provides open source APIs, libraries, and agents to collect traces and metrics for application monitoring. The AWS distro for Open Telemetry consists of collectors that are built into the application and exporters that send data back to backend analytics targets. In addition to supporting AWS targets like CloudWatch and X-Ray, customers can also send traces and application metrics to a number of AWS partners and third-party providers. The distro for Open Telemetry simplifies the process of collecting data by allowing you to instrument your applications just once, instead of using multiple tools from different vendors to collect metrics and traces. We're excited about the Open Telemetry project, and in addition to providing this distribution, we're also contributing to the upstream project for a number of components. Now, no matter how you choose to log, monitor, trace, and alert, There's a tool that fits your needs. We covered a lot of ground today. We talked about the importance of development, how to build dependable applications, and how to effectively run them. If you paid close attention, you'll notice there has been a trend with all these things. More and more, AWS is taking tasks that have been slow, difficult, or time-consuming and making them easier to use by using advanced technologies to simplify them. These technologies can include automated reasoning or even machine learning. Take this AWS Panorama appliance, for example. This device allows you to deploy machine learning models to existing industrial cameras, like the ones that will be here in this factory. With this device, a business could run computer vision models for tasks such as quality control, or part identification, or security, or workplace safety. And this isn't changing any of the processes that weren't already done, but it's improving them and allowing the operators who perform them to run more efficiently. Or there's Amazon Lookout for equipment, a machine learning service that detects abnormal equipment behavior using IoT sensors. As technologies advance, you'll continue to see these technologies improve our work, such that we all can be more efficient. At AWS, with every new service we build, we ask how we can make it better by using machine learning. And you can see this in many of the services we've released over the past few weeks around databases, security, and operations. These aren't machine learning services, but they're services enhanced by machine learning. Amazon isn't alone in doing this. Just like Eva, businesses around the world are integrating machine learning with existing applications and data to get more value out of what they already have. As technology that powers our work advances, we'll continue to chip away at the heavy lifting that we all do on a daily basis. So as you're building or using a system, take a few minutes to think about which parts can evolve from simple automation and can make use of advanced technologies such as machine learning. You might be surprised by all the places that ML can help. When we started today, we talked a lot about how AWS is meeting developers where they are. And what if we applied machine learning to that? Services like Amazon Code Guru were built to solve problems exactly like this. When you're writing software, there are a lot of things that need to be checked. Problems like memory leaks or hard-coded credentials and duplicate lines after refactoring, which won't prevent your code from compiling, but can still cause problems for your application. Typically, these problems are identified during manual code reviews before branches are merged. But these are difficult tasks, and some vulnerabilities are easy to miss, especially if there are many changes that are happening at once. And that's why we built Amazon Code Guru. Code Guru uses machine learning to automate code reviews during application development and to profile applications after they've been deployed. As code is checked in, Code Guru Reviewer will automatically review your code, just like a senior engineer on your team would do. It provides advice on what's wrong and gives you links to documentation. And what's great about how it works is that it does these checks automatically when you check in the code, just like you would do with another code review. This way you can find and fix problems early, and the code reviews performed by members of your team can focus on more important aspects of your business logic. Code Guru Profiler, on the other hand, attaches to running applications in your test or production environment. Using machine learning, it inspects your running applications in order to find performance bottlenecks. It allows you to troubleshoot latency and CPU utilization issues, learn where you can reduce infrastructure costs, and identifies application performance issues. By combining automated reviews from Code Guru With the learnings from AWS Fault Injection Simulator and the recommendations from DevOps Guru, we can improve the entire development lifecycle using machine learning. And this is just the beginning. There are so many parts of application development that involve writing and rewriting bits of our applications that are essentially just plumbing and aren't any business value. As the tools we use advance, machine learning is going to continue to remove undifferentiated heavy lifting of building software. Like machine learning, another field I'm getting really excited about, and that I think is going to change our assumptions about what's possible in the world, is quantum computing. I know, we've been hearing about quantum for years now, and how it will be the next big thing. I truly believe that at some point it will become the next game-changing technology. It's going to happen slow at first, providing small optimizations and enhancements, but eventually it will revolutionize the areas it is well suited for. Chemistry research, drug discovery, material sciences, they're all going to be some of the first industries that will benefit from quantum computing. Just like GPUs have changed the field of machine learning, I believe that quantum processors will eventually do the same for many of these scientific fields. AWS is investing heavily in quantum. Our Quantum Solutions Lab connects experts with organizations to build internal expertise and strategies required to run quantum workloads. The AWS Center for Quantum Computing is a partnership with Caltech, where we are researching quantum computing algorithms and hardware. Just last week, our scientists published a new research paper showing a theoretical quantum computing system with groundbreaking improvements in error correction. We also launched Amazon Braket, which democratizes access to quantum resources from a number of providers. And this is where the power of the cloud really shines. A popular use case of Braket is for developers to learn to evaluate if quantum could enhance their workloads as it advances. Historically, you'd have to wait for technology like this to leave the research phase, be turned into a mass-produced product, and purchased at enormous cost. Only then would you be able to determine if it would actually help you. By making quantum computers and expert assistants available to every developer today, we're helping AWS customers stay one step ahead. As a software developer, now is the time to start thinking about quantum computing. It is the ways that we're starting to see machine learning make an impact on our daily lives. And the future that technologies like quantum computing will enable that make me so excited about cloud and technology as a whole. And I'm excited to see how developers will use these technologies to truly improve the world around us. I want to thank you all for spending time with me today as we explore this amazing space for my favorite city. This year has been challenging in a lot of ways. But I also believe that challenges are the best time to reflect and think about whether you are building the right services for your customers. We've talked about how AWS is meeting developers where they are, and that's because you are our customers. As you develop your applications, think about what you can do to meet your customers where they are. Many of us have experienced severe anxiety and uncertainty about the future in the past year. Uncertainty about our jobs, health, financial future, family, and much more. I strongly urge our customers, for example, those in financial services, to be conscious about this when they build new ways to engage their customers. Address these important issues up front and let them come back, for example, in the way you design your interfaces. Or what services you could build for your customers that help them in addressing their uncertainty. For almost all of us, digital services have become essential. But this means that these services are not just for the digital natives with their fiber connections and the latest smartphones. Consider the experiences you're building for them and how they access them. Not everyone has 5G or even a strong Wi-Fi connection at home. If you build essential services, make sure they also work on low bandwidth, high latency connections. There are enough news reports of kids having to go to a parking lot of a grocery store or a fast food restaurant to just get a decent internet connection for school. The applications you build are essential for your customers. Whether you're building a service that helps people budget what they have and helps them predict their immediate financial future, or maybe you're building a website that helps people stay connected to each other when they wouldn't be able to otherwise. We, as developers, have a responsibility to our customers to build the best applications we can for them in ways that take their current reality very seriously. It's never been a better time to use your knowledge, skills and talents to make a difference in the world. Now, go build.